Mechanisms of electrode-induced injury, Part 3, Practical Concepts and Avoidance. These descriptive graphics and animations are intended as a supplement to our written article published in the American Journal of Electroneurodiagnostic Technology in December 2007. The authors wish to thank the ASCT staff, particularly Maggie Marsh-Nation and Lucy Sullivan, for making this online presentation format possible. Slide 2. The goal of this graphical presentation is to further illuminate the mechanisms behind the most common electrode-related lesions as discovered in our literature review, which was published in our second article in February 2007 in the AJET Journal. Three primary causes of electrode lesions are discussed, including radiofrequency energy lesions, electrochemical lesions, and pressure points. In addition, ground loops and isolated amplifiers will be discussed. Before we begin, there are some electromagnetic principles that are very important to understand. Let's have a look. Slide 3. When generating electrical current, it doesn't matter whether you're referring to a huge power station generator, like this at the bottom of a dam, or a small handheld generator. The same basic physics principles apply. Slide 4. When you move, or in this case rotate, a wire through a magnetic field, you generate a current in that same wire. In this instance, we moved a wire through a stationary magnetic field. But what about the instance where the magnetic field is moving and the wire is stationary? Slide 5. In the event that the magnetic field is moving through a stationary wire, like in this animation, you get the same result: current in the wire. Slide 6. So as we begin our discussion on electrode lesions, remember, a changing magnetic field will create a current in nearby wires. Also, moving wires near a stationary magnet will create a current in the wire. So, either changing magnetic fields or radio wave energy can create current in wires, such as our lead wires. Slide 7. Let's discuss radio frequency energy lesions. First, from the electrosurgical unit, commonly referred to as the BOVI. Using large amounts of electrical energy, the ESU is designed to heat or cauterize tissue, so it inherently offers risk for burns. Our electrodes can represent an unwanted pathway back from the active ESU electrode to the ESU return pad. Electrothermal burns can result. How do these burns occur? Let's take a look. Slide 8. The ESU uses pulses of electricity at very high frequencies, near 300 kHz, to cut and cauterize tissue in the surgical site. This very large volume of electrical energy passing through the very small surface area of the active ESU probe creates enough current density to cauterize tissue. When watching it, you can actually see the electrical arc between the active probe and the patient's tissue. At the other patient connection, the ESU return pad, there is a very large surface area, resulting in very small current densities so that no damage to tissue should occur. The ESU functions based on the fact that the electricity from the active probe wants to return to the return pad, completing the electrical circuit. Which path will it take? The desired intended return path is the body, but it is important to remember that the electrical current will follow the path of least resistance, even if the path of least resistance is some unwanted pathway near or on our patient. Slide 9. Here is one scenario where our electrodes could present an unwanted path of low resistance to the ESU energy. Here is one of our recording electrodes. In this case, let's say it is a subdermal needle electrode placed in the vastus lateralis on the same side as the ESU return pad. In this scenario, our electrode lead wire could be close to the return wire of the ESU return pad. What does impedance for a capacitor do as frequency increases? The impedance decreases, right? At the very high frequency of the ESU, the impedance of the capacitive coupling between our electrode and the ESU return wire could be low enough to allow substantial current to flow on our lead wire and ultimately to the patient through our subdermal needle, which only has approximately 15 square millimeters of surface area. This is a recipe for an electrothermal burn at the site of the subdermal needle. Does having the electrode lead wire closer to the ESU cable make the capacitive coupling worse? Yes, it absolutely does. Does it matter if it is the ESU active cable or the ESU return cable? No, it does not. The possibility for capacitive coupling between our electrode lead wires and the active ESU cable is the same as the possibility for capacitive coupling between our electrode lead wires and the ESU return cable. Could these unwanted current pathways create electrode burns? Yes. As mentioned, lowering the surface area of the electrode in contact with the patient's tissue increases the chance of an electrothermal lesion due to high current density. Slide 10. Here is another scenario where our electrodes could present an unwanted path of low resistance to the ESU energy. You are in surgery with your electrodes attached. Here is one electrode for demonstration purposes. Notice the ESU tip is away from the patient. What happens if the surgeon fires the ESU tip away from the patient? A blast of RF energy fills the air. This discharge can be up to 10,000 volts at 300,000 hertz frequency. And it is looking for a return to where? It is looking to return to the ESU return pad. What does our electrode lead wire look like to this RF energy? An antenna. What happens if we loop our lead wires? The RF energy sees it as a coil, and the lead wire picks up the energy, or you could say is electrically induced more. Coiled lead wire creates increased chance of electrothermal electrode burns from the ESU energy. Slide 11. In summary, the ESU can create electrothermal electrode burns from radio frequency electrical energy from two mechanisms: capacitive coupling between our recording or stimulating electrode lead wires and the ESU cables. Second, unwanted ESU discharges away from the patient, allowing the radio frequency energy to return to the patient through the air and seeing our recording or stimulating electrode lead wires as antennas. Keeping our electrodes and electrode lead wires as far away from the ESU cables and return pad and keeping our electrode lead wires uncoiled decreases the risk of electrothermal burns. Slide 12. Next, let's discuss radio frequency energy electrode lesions associated with MRI. The MRI, in order to image, uses static and pulsed magnetic fields as well as pulsed radio frequency energy at very high frequencies. As we have already seen, changing magnetic fields, or RF energy, can create current in electrode lead wires. As with the RF energy associated with the ESU, electrothermal burns can result. How do these burns occur? Slide 13. This animation shows an extremely simplified depiction of what occurs with an MRI scan. The body has untold billions of hydrogen atoms, each of which contains a polarized proton in the nucleus. A very strong magnet, the main magnet, is used to align these hydrogen protons, with roughly half in one direction and half in the other, canceling each other out. But it's never quite 50-50. The trick of the MRI is to use much smaller magnets from the side that can alter the direction of these non-canceled hydrogen protons in a specific direction. A pulse of radio frequency energy at a frequency specific to the hydrogen proton is then used to impart energy to the proton that helps image or see it on the MRI scan. MRI is a complex topic, and the discussion will be limited here to contributions to electrode lesions. Let's look closer at each MRI component. Slide 14. The MRI machine is functionally a tube that the supine patient enters for scanning. MRI safety procedures are extensive, and placement of electrodes on the patient during the scanning process is but a small portion of the overall set of safety considerations. Let's go inside the machine for a closer look. Slide 15. Let's start from the inside out with the bore of the machine. Slide 16. The bore is the tube which the patient enters. The MRI can image in any plane, including the axial or transverse axis, which images inferior-superior, the sagittal axis, which images left-right, and the frontal or coronal axis, which images anterior-posterior. Several magnets and one source of RF energy are used to accomplish this imaging. Slide 17. The main magnet creates a very strong magnetic field along the axial axis. As already mentioned, this field aligns the slightly polarized protons of the billions of hydrogen atoms in the body into alignment with the main magnet field. The main magnet is very, very strong, but it is static and does not alternate its direction or magnitude. To help give an understanding of how strong the main magnet is, if 1 millitesla is 1 inch, 3 teslas is the height of a giant redwood tree, and the Earth's magnetic field is roughly the height of a tiny ant. To get this enormous magnetic field requires a very large amount of wire coiled around the bore of the magnet, supercooled to 452 degrees Fahrenheit below zero. Remember that when wires move through a magnetic field, a current can be generated. Do electrodes attached to a patient in movement in the main magnet represent potential danger? Yes, but the risk is low compared to other MRI risks. The main magnet is not a likely source of electrode burns. Slide 18. Remember the smaller magnets that alter the main magnet field? The axial gradient magnet creates very small fluctuations to the main magnetic field in the axial plane at a rate of around 1 kilohertz, a relatively low frequency. This small fluctuation is necessary to allow a three-dimensional view. This fluctuation is created by the axial gradient magnet coils illustrated here. The axial gradient magnet is very weak, approximately 24 milliteslas. If 1 millitesla is 1 inch, 24 milliteslas is the height of a car tire. Remember that the main magnet would be the height of a giant redwood tree. The gradient magnets are very small compared to the strength of the main magnet. Remember that a changing magnetic field can create a current in nearby wires. Do electrodes attached to a patient in presence of the axial gradient magnet represent potential electrode burn danger? Yes, but the risk is very low compared to other MRI risks. The gradient magnets are not a likely source of electrode burns. Slide 19. The second of the smaller magnets is the frontal gradient magnet, which creates very small fluctuations to the main magnetic field in the frontal plane at a rate of around 1 kilohertz. Again, this small fluctuation is necessary to allow a three-dimensional view. This fluctuation is created by the gradient magnet coils illustrated here. And just like the axial gradient magnet, the frontal gradient magnet is tiny, approximately 24 milliteslas compared to the main magnet, like the tire compared to the giant redwood tree. And the frontal gradient magnet too has relatively low risk for electrode burns. Again, the gradient magnets are not a likely source of electrode burns. Slide 20. The third of the smaller magnets is a sagittal gradient magnet, which creates very small fluctuations to the main magnetic field in the sagittal or side-to-side plane at a rate of around 1 kilohertz. Again, this small fluctuation is necessary to allow three-dimensional view. The fluctuation is created by the sagittal gradient magnet coils illustrated here. And just like the axial gradient magnet, the sagittal gradient magnet is tiny, approximately 24 milliteslas compared to the main magnet. like the tire compared to the giant redwood tree. And the sagittal gradient magnet too has a relatively low risk for electrode burns. Again, the gradient magnets are not a likely source of electrode burns. Slide 21. The RF pulse coil bathes the bore of the MRI with a pulse of radio frequency energy at the very high frequency of 63 MHz, actually 63.87 MHz. When this specific frequency of energy is imparted to the non-cancelled hydrogen protons, it causes them to spin. When the pulse stops and the spinning slows, the energy released can be measured, which can be turned into an MRI image. There are many different sizes of RF pulse coils, some designed for specific body parts, such as the example shown here. Considering any electrodes with lead wires that might be on the patient, remember, impedance due to capacitive coupling decreases dramatically with increasing frequency, and 63 million or 63 megahertz is a very high frequency. To this RF energy, our electrode lead wires look like antennas. As a result, significant electrode burns can result. The RF pulse coil is the overwhelming source of electrode burns from MRI. Slide 22. In summary, MRI can create electrode-related electrochemical lesions from radio frequency electrical energy delivered from the very high frequency RF pulse coil. Slide 23. Next, let's discuss electrochemical electrode lesions. When direct current is applied to tissue, chemical reactions can occur at the anode and cathode. Electrochemical burns can result. How do these burns occur? Let's take a look. Slide 24. Here is an animation of a typical bar electrode used to stimulate the wrist, but let's use constant current instead of the pulses normally used. When DC current is applied to skin, two things occur. Acidic buildup under the anode and basic or alkaline buildup under the cathode. Each is capable of creating an electrochemical burn in a short time. We'll need to take a closer look at the tissue to understand why. Slide 25. Here we have an arm with 3 electrodes applied, 1 surface plate electrode and 2 subdermal needle electrodes. If we take a closer look at the tissue level, we see that the metal of the electrode is full of electrons, and the tissue is full of charged particles. In electrodes, electrons are the charged particles that move to make current flow. In tissue, ions or electrolytes are the charged particle that moves to make current flow. Slide 26. Let's take a closer look at the electrode tissue interface. Let's apply the metal surface electrodes. The metal electrodes are full of electrons waiting to be used as current. In the tissue, sodium chloride, NaCl, and water, H2O, dissociate into sodium ions, Na+, chloride ions, Cl-, hydrogen ions, H+, and hydroxyl ions, OH-. Slide 27. When we apply a direct current to the electrodes, one becomes anode and one becomes cathode. The anode has a positive polarity and the cathode has a negative polarity. Will the negative ions in the tissue be attracted to the anode? Yes. Will the positive ions in the tissue be attracted to the cathode? Yes. And the ions tend to migrate towards where they are attracted, so you wind up with a pool of negative Cl- and OH- ions at the anode and a pool of positive Na+ and H+ ions at the cathode. These pools of ions, given time, can yield the following chemical reactions. Slide 28. At the anode, 2 water molecules yield harmless chemical species. At the cathode, 4 electrons react with 2 water molecules to yield harmless chemical species. At the anode, hydrogen ions and chloride ions react to form hydrochloric acid, HCl, a dangerous acid. At the cathode, Sodium ions and hydroxyl ions react to form sodium hydroxide, NaOH, a dangerous base. The longer the direct current is applied, the greater the buildup of these harmful reactants. The greater the intensity of the direct current, the greater the buildup. Slide 29. In summary, direct current can create electrode-related lesions due to electrochemical reactions. When direct current is used, the inherent positive electrode, anode, and negative electrode, cathode, tend to create pools of oppositely charged ions in the tissue under them. If duration and current are large enough, chemical reactions can yield acidic at the anode and basic at the cathode buildups under the electrodes. It is important to note that in neurodiagnostics, we rarely use direct current. We overwhelmingly use very short duration pulses with relatively long interstimulus intervals, which tend to avoid significant buildup of these harmful reactants. It is very important, however, to be watchful of potential DC leakage current, which could come from our equipment if not properly monitored by the correct biomedical staff, or which could come from batteries that are part of faulty circuits or equipment. Finally, biphasic stimulation has been shown to reduce the processes which yield the harmful reactants associated with direct current stimulation. Slide 30. Let's discuss pressure point lesions. What is the problem? First, external pressure can damage tissue. Remember that on average, under normal conditions while sleeping, people adjust their body position up to 18 times per night. One of the reasons for this is the body's natural response of avoiding pressure-related injuries, including injuries to skin. Second, our patients are heavy. Not just total body weight, but segmental body weight is important. Third, the electrodes we use can create pressure-related injuries. Electrode dimensions are very important if our patients will be lying on them for any length of time. Slide 31. Let's have a look at external pressure. Under light pressure, the results include slightly increased tissue perfusion and low risk for lesion injury. How much pressure is light pressure? Experimental models in rats indicate that pressure less than 0.27 pounds per square inch is light. Theoretical models indicate that pressure less than 0.48 pounds per square inch is light. Under heavier pressure, the results include rapid drop-off in tissue perfusion, increasing risk for pressure-related lesion injury. How much pressure is heavy pressure? Experimental models in rats indicate that pressure greater than 1.2 pounds per square inch is heavy. Theoretical models indicate that pressure greater than 0.97 pounds per square inch is heavy. To understand these numbers, a helpful hint is that a square inch is approximately the size of a quarter. Let's have a look at segmental body weights. Slide 32. So how much do different body parts weigh? Using cadavers, the body weight percentages of body parts for an average-sized adult have been experimentally determined. Assuming a 150-pound patient, the head weighs 11 pounds, the trunk weighs 76 pounds, the upper arm weighs 4 pounds, the forearm weighs 2.5 pounds, the hand weighs 1 pound, the thigh weighs 15.5 pounds, the calf weighs 6.5 pounds, and the foot weighs 2.5 pounds. Next, let's look at electrode surface area. Slide 33. How much surface area does an electrode have? As an example, let's look at a typical EEG cup electrode. A typical EEG cup electrode is 10 millimeters in diameter, yielding a surface area of 79 square millimeters. But let's have a look at the underside of the cup. A closer look at the contact surface of the cup itself reveals that only a ring around the periphery of the cup actually makes physical contact with the patient. The ring is typically around 2 millimeters thick, meaning that the real surface area in physical contact with the patient is not 79 square millimeters, but actually only around 50 square millimeters. Slide 34. Let's bring the segmental body weights together with electrode surface area. Consider the situation where a given body segment happened to have its entire weight on that EEG cup we were talking about with 50 square millimeters of surface area. Would this realistically ever happen? Probably not, but it helps illustrate the concept of electrode pressure. Again, considering a 150-pound patient, the pressure created by the electrode under the head will be 141 pounds per square inch. Under the trunk will be 978 pounds per square inch. Under the upper arm will be 50 pounds per square inch. Under the forearm will be 31 pounds per square inch. Under the hand will be 14 pounds per square inch. Under the thigh will be 199 pounds per square inch. Under the calf will be 83 pounds per square inch. Under the foot will be 29 pounds per square inch. Note that all of these segmental body weights could theoretically create pressures much greater than the 1.2 pounds per square inch discussed previously to be unsafe heavy pressure. Even the hand, which segmentally only weighs 1 pound, creates a theoretical maximum pressure under the EEG cup that is over 10 times the theoretical unsafe pressure. Slide 35. Clearly, we place different types of electrodes on our patients. Just a few examples include subdermal needle electrodes, surface plate electrodes, EMG needle electrodes, EEG cup electrodes. At times, our patients might even have their body weight on our wires or connectors. Each electrode type has its own distinct physical profile. While this article is not the place to go over the surface area and pressure-related risk of each type of electrode, certain characteristics are, however, intuitive. Specifically, sharp edges in contact with patients increases risk of skin pressure lesions. Smooth edges are preferable, and flatter profiles in general offer decreased risk for pressure lesions. Slide 36. Is there more to consider than just pressure? Absolutely. Keeping the pressure duration to less than 29 psi minutes reduces the risk of pressure-related injury. Remember the case where the patient's hand, weighing roughly 1 pound, lies on the cup electrode with 50 square millimeters of surface area in such a way that all of the weight of the hand is on the cup, as illustrated here. According to the information above, how long could the patient theoretically lie on this position with reduced risk? Approximately 2 minutes, a very short time. Slide 37. In summary, pressure to our electrodes can create mechanical lesions. Low-profile electrode surfaces with smooth edges are preferable. Longer durations of pressure application dramatically increase risk. While it is true that our patients would rarely have their entire body weight on an electrode, the point is clear that we need to be mindful of our electrode's location and for how long the patient's weight is on them. Slide 38. Lastly, we will discuss ground loops and isolated amplifiers, because ground loops have traditionally been feared but frequently misunderstood. While ground loops are a safety concern, the isolated amplifiers of current equipment designs significantly decrease the relative risk. Slide 39. A basic review of the electricity from wall outlets is a good place to start. Remember that rotating the coil of wire through the magnetic field generates a sinusoid current in the wire. This is basically how the voltage we get from the wall is generated. There are 3 connections in the wall socket correlating to 3 electrical sites. The hot line is alternating sinusoidal voltage. Notice that the hot connection in the socket is smaller and therefore harder to electrify an errantly placed object. The neutral is just that, electrically neutral. Remember, without a reference, the hot line would not be able to complete an electrical circuit. The ground is just that, the earth, and is frequently called earth ground. The ground connection in the wall outlet is connected by a very thick wire to all of the other ground connections in the building and is usually connected to water pipes that go down into the ground underneath the building. It is worth noting that the neutral connection is frequently connected to the ground connection at the wall socket, but not always. Slide 40. Let's consider some of the basics of our AC power. Why can birds sit on power lines without getting shocked? They aren't grounded. They are only touching one side of the voltage. The circuit is not complete. What would happen if a bird could touch both the neutral and hot lines at the same time? Well, you get the picture. The bird that touched both neutral and hot lines completed the circuit and was shocked. Slide 41. Would the same thing work for humans? You bet. Is it easier to touch a grounded piece of metal in the operating room or touch the hot voltage line? Most equipment is grounded. It's much easier to touch ground than to touch the hot connection. Most electrical fixtures and much metal in any structure is frequently grounded. Why do we use a ground on the patient if it means they can get shocked easier by the hot line? One big reason: leakage current. Slide 42. This illustration helps understand patient safety concerns with leakage current. The top piece of operating room equipment represents an ungrounded machine. Notice that the equipment chassis, the actual equipment case, is not connected to ground. The bottom piece of operating room equipment represents a grounded machine, which has a physical connection between the chassis and the wall outlet ground. Both machines have isolation transformers which use coils to physically separate the input wall voltage, the hot voltage, from the output coils, as well as step down the wall voltage to a lower voltage that is then used to power the components inside of the equipment. The current flow shown represents the electrical activity inside of the equipment. In the event of an electrical short, the equipment chassis can be exposed to some or even all of the high input voltage from the wall outlet hotline. When that occurs, the leakage current is looking for a pathway to flow. In the top piece of equipment that is not grounded, the current does not have a pathway to flow and is illustrated here as a pulsing red energy waiting for somewhere to go. In the bottom piece of equipment that is grounded, the current does have a place to go and does flow from the equipment chassis back to the earth through the grounding wire. What if a patient who is connected to earth ground touches the ungrounded piece of equipment? The patient gets shocked, and the leakage current goes through the grounded patient, in this instance in a very dangerous fashion since it goes through the patient's chest and torso. Note that currents as low as 0.1 milliamps can create ventricular fibrillation with electrically sensitive patients, and currents as low as 100 milliamps can create ventricular fibrillation in normal patients. What if a patient who is connected to earth ground touches the grounded piece of equipment? In this instance, the patient is happy. While the patient still represents a potential pathway to ground for the current, the patient is a very high impedance pathway to ground in comparison to the very low impedance ground wire attached to the chassis. The leakage current goes through the ground wire, not the patient. Slide 43. This illustration will help understand what a ground loop is. We have a patient that is connected to ground from two different pieces of operating room equipment. In this example, let's assume that the two different pieces of equipment are far apart in the operating room and plugged into wall outlets on opposite sides of the room. Remember that the ground wires from all of the outlets in the building are connected together? Well, there is a thick wire connected between the two different ground outlets illustrated here. For the illustration, let's assume that in the next room there is a heavy piece of equipment, such as a laboratory high-power heating oven or some heavy motor operating, that has a large amount of leakage current running through the ground wire, illustrated here. What does any wire have? Every wire has some resistance, right? What happens when a current flows through some resistance? Some voltage buildup, right? What does this voltage do? It drives a current through a circuit. Do you see a potential circuit? There is a circuit that passes through each outlet ground and ultimately through the patient. This is a ground loop. In this instance, as the last one, the current flows in a very dangerous fashion through the patient's chest. One important note here. In this particular instance illustrated, would it matter if the equipment was even on? No. As long as the ground connections were applied to the patient and the equipment was plugged into the wall outlets, this ground loop could occur whether the equipment was on or off. Another important note here is that the ground electrodes connected to the patient in this instance are actually connected to ground at the wall outlet through the equipment. As we will see in the next slide, that is not always the case. Slide 44. Now let's consider our particular neurodiagnostic equipment and the connection we often call ground. Illustrated is a piece of IOM equipment. Here is our patient. Here are our amplifiers. Here are our multiple lead wires connected to the patient. Here is the amplifier box ground connected to the patient. On modern IOM systems, are your amplifiers and electrodes electrically isolated from your IOM machine? They absolutely are, usually optically isolated. On modern IOM systems, is the amp box ground the same as the IOM machine ground? No, they are not. The amp box ground is electrically isolated from the IOM machine, just as the amplifier connections are. In summary, if direct earth ground connection is used, dangerous currents can flow through our patients from leakage current and ground loops. Modern neurodiagnostic equipment, isolated amplifiers, and isolated grounds greatly reduce the risk of these dangerous currents. Slide 46. In conclusion, we hope that these illustrations have helped convey the causes of electrode-related lesions from radio frequency energy from electrosurgical units or MRI, direct current, and pressure points. We hope that you consider the electrode-related injury avoidance fundamentals list included with the written version of the third and final article of this series. And finally, please be careful and monitor your patients to make sure they are not receiving preventable electrode-related lesions. Thank you and good luck.